All right, so what we started to do last class was we started to do chapter 3. I think we spent about 20 minutes or so on chapter 3. And we started to talk about basic concepts of probability. We said that it was important to start looking at probability because once we get to inferential statistics, once we start having to make an inference about something, that there's a likelihood that our inference could be correct and there's a likelihood that our inference could be wrong. And therefore there's a probability associated with our inference, right? So as we start working our way towards inferential statistics, it's important that we stop at the concept of probability along the way. And once we started to do chapter 3, we realized that the first couple of things were nothing but some definitions. First one that we went over was a random experiment. Random experiment is simply just some experiment where you don't know the conclusion in advance, like rolling a die, pulling a number out of a hat. Sample space had to include all possible outcomes of your experiment. So like if we rolled a die, then our sample space was the number 1, 2, 3, 4, 5, and 6, because those are all possible outcomes. If we flip a coin, it's going to be like heads and tails. That's going to be our sample space. Now the individual outcomes in our sample space, so like again, if we're rolling a die, the numbers 1 through 6, those are outcomes. And if we have some subset of outcomes, like if we take the numbers 1 and 2, that's what we're going to consider to be our events. Okay? We can define our sample space to be whatever we want. Suppose we said, what are the grades that you could get in this class, and then we could take some event of those grades, like passing versus failing, and then obviously those events would just include the different grades. All right, is everybody good with that concept so far? Then we also look at the probability of an outcome. We said that probabilities of an outcome, there's a couple of probabilities that are associated with outcomes. What's one probability that we know for an outcome? This was yesterday wherever I started talking about like your weather app, right? Whenever you look at the percentage of rain on your weather app, what are the types of percentages that you're going to see? 0 to 100, right? So we know that the probabilities of outcomes can go as low as 0, can go as high as 1, or 0% and 100%, or anything in between. We're never going to get a probability of an outcome that's less than that, less than 0, or anything that's greater than 1. Right? Does that make sense to everybody? Then another thing that we said as well is if we have some event, right? Like up here we have 1 and 2 inside the event E, and 1 and 2 are just outcomes that are in our sample space. If we wanted to calculate out the probability of this entire event, then what we would do is we would add up the probabilities of each outcome in that event. So therefore, if 1 had a probability of 1/6, and 2 also had a probability of 1/6, then the way that we can figure out the probability of event E, so of this entire box, would just be to take 1/6 plus 1/6, and that would be obviously 2/6 or just 1/3. Right? So the way that we calculate out the probability of an event is to add up the probabilities of all the outcomes in that event. Everybody good with all this stuff so far? All right. Then the last thing that we said, and we kind of knew this by intuition last class, was if you take all possible outcomes, so here again, the example of a die would be 1, 2, 3, 4, 5, and 6. And you add up the probabilities of all of the outcomes in your sample space, then all of those have to equal 1 or 100%. Right? You guys knew that by intuition last class when I said, hey, if I roll a 6-sided fair die, what's the probability of getting 3? You guys immediately told me that it was going to be 1/6. Right? And so you guys did that by intuition. You said I'm going to take 100%, I'm going to divide it by 6 possible outcomes that I can get, so each one's going to have a probability of 1/6. So therefore, if you add them all up, then you're going to always equal 1 or just 100%. Then the last thing that we started to talk a little bit about last class, we also did an example of it, was a Venn diagram. A Venn diagram here is usually depicted, especially in this class and in the textbook associated with this class. They're usually rectangles, and we're going to signify that this rectangle is our sample space. What signifies that this rectangle is our sample space? that little S in the top corner, right? Sometimes it's here in the top right, sometimes in the top left, or just somewhere in this box, but it's usually up here in the top right in your guys' textbook to signify that this is the sample space. Then, inside the sample space, we're going to record all possible outcomes, right? Again, here we have the example of rolling a six-sided die. So therefore, somewhere in this rectangle, we're going to have the numbers 1, 2, 3, 4, 5, or 6, right? Just like I said last class, it doesn't matter if you write them in order, it doesn't matter if you write them in reverse order, or if you just have them somehow floating around like I do up here. As long as all 6 of those numbers are inside there, then that's a perfectly fine Venn diagram. Right? Everybody good with this? Then what we said is we can create events for different scenarios in this Venn diagram. Here, event A, we said was going to contain all even numbers. And the way that we depicted an event is we simply just made a circle or some kind of circular shape around the numbers 2, 4, and 6, since those are the even numbers. And to show in our Venn diagram that this is event A, we just have like this capital A that's somewhere close to that circle. Right? Same thing with event B. Here we said that event B contains all high numbers. We assumed that the high numbers were going to be 4, 5, and 6. So then therefore here we have another circle around the numbers 4, 5, and 6. And we had a capital B next to that circle to show that that was event B. And that's as far as we got last class for chapter 3. Everybody good with where we left off last class for chapter 3? All right, then let's continue with example B here. It's asking us what is the probability of rolling a 1? So the way that we're going to write this here is this. So I'm going to introduce some new notation here. When it's asking you to find the probability of something, the way that we write the probability of something is we have a capital P, and then we have these brackets. So whenever in this class you see the words probability of, you can immediately write down P in parentheses, and you know that you're on the right track, right? So later on we're going to start doing some problems, and these problems are going to say find the probability of something. We're going to try to put numbers up here. We're going to start to calculate out numbers. But the first thing that we're going to try to do is we're going to try to take that English expression and write it in terms of math symbols. And if we can make that first step, once we get to the math symbols, we're just going to follow a simple procedure, and we're always going to come up with the number that we're looking for. Right? So the first step is always take the English sentence and convert it to a math symbol. Whenever you see the probability of, you write P and then these two parentheses. And then whenever you're trying to find the probability of, you just write inside these two parentheses. Right, is everybody good with that? So if we're trying to find the probability of 1, we can either just write the number 1 in here and say, hey, we're trying to find the probability of 1. Or here, just to be super explicit about it, I'll say that we're finding the probability of rolling a number 1. So what I'll do for the first couple times that I write this is I'll write rolling 1 in here. But after we do a couple of examples, you guys are starting to get the gist of it. I'm just going to write the number 1 here. All right, so now let me ask you guys this. We're rolling a six-sided fair die. What's the probability of rolling the number 1? Cool. Then the next thing is asking us to find the probability of rolling a 2. So the probability of rolling the number 2 is equal to? And so on and so forth. This is something that we already said last class. So again, up here I'm just going to make a dot, dot, dot. And finally we're going to find the probability of rolling a 6. So now I'm just going to leave the rolling thing away. And I think everybody will agree that there should also be 1/6. Everybody good with this so far? All right. Well, now it's also asking us to find the probability of event A. So here I'm going to have the probability of, and now in here I can write event A. Or just like I did up here with rolling, what I'm eventually going to do is I'm just going to write the probability of, and I'm just going to put a capital A here and just leave the event away. You know, mathematicians and statisticians always like to be very precise but also very brief. So I'm just writing event right here to be really, really explicit about it. But especially even later on today, I'm just going to start writing P parentheses, capital A, and close parentheses, because there's no sense in writing that event if we already understand that A is an event. All right, so if I wanted to find the probability of an event, how do I find the probability of an event? I'm hearing two people talk. How do you find the probability of an event?
You add the probability of all of the different possible outcomes that would be that event.
Awesome. So we're going to add up the probabilities of all of the outcomes in that event. So what outcomes are in event A? 2, 4, and 6. So then that's going to be equal to the probability of 2 plus the probability of 4 plus the probability of 6. Is everybody good with this? So here then we're going to have this is equal to 1, 6 plus 1, 6 plus 1, 6. And this is 3, 6, or just 1/2. Is everybody becoming a little bit more familiar with the notation? Like I know that the math to this right now is like mind-numbingly easy, right? We're just adding up 6 here, right? But is everybody getting familiar with the notation? That's the most important part about this so far. All right, then the next thing that we're trying to figure out is the probability of event B. Take like 30 seconds for yourself and see if you can write this down similar to how I have it written up here for the probability of event A. What's your last name? Everybody good with this? Any questions? All right, let's do it together. So then we have the probability of event B is equal to the probability of the number 4 plus the probability of the number 5 plus the probability of the number 6. And just like we had before, we're going to have 1, 6 plus 1, 6 plus 1, 6, which is 3, 6, or 1/2. All right, any questions whatsoever about notation? All right, then let's go on to start talking about complements and intersections. All right, complements and intersections. Complements and intersections are really, really, really important stuff. This is going to be what the vast majority, or at least half of your homework is going to be on, complements, intersections, and unions. So if you have any questions about the stuff as I'm going through it, please make sure that you ask those questions. So first, what's the definition of a complement? So we're primarily going to look at complements of events. And if you remember before, an event in our Venn diagram was simply just all the stuff that's in like some circle A, right? Well, the complement of A is anything that is in S, anything in our sample space S, that is not in event A. So, therefore, anything in here anything that's in this shaded region is in the complement of A, right? So again, the complement of A is anything that is inside of S that is not in A. The symbol that we use for the complement is kind of like a little C in the exponent. Some books will have it where you have a complement. It'll just be like a little apostrophe. Those are A complements. Any questions about A complement? So, how does this help us? Well, suppose that we're trying to find the probability of A complement, right? So we're trying to, again, find the probability of anything in this shaded area over here, anything that's not in A. Well, if we know what the probability of A is, then we can just take 100% minus the probability of A, and that's going to give us everything in A complement. Right? Does that make sense? Like, if I say, let's say that event A is everybody who passes this class, right? Then I say that there's a 90% chance that you're going to pass this class, right? Everybody go with that? That's event A. What is A complement? 10% for everybody that fails this class, right? And the way that you got 10% was that you said, well, if passing this class is A, then A complement is failing. If you're going to pass with 90%, then failing is going to be 10%, right? And that's exactly what this formula is saying right here. If you're trying to figure out the probability of A complement, you can take 100% minus the probability of A, and that's going to give you A complement. Make sense? All right. Then let's consider the example above that we were dealing with a six-sided fair die. What is a complement? So again, going back to the example that we just got done doing. Good. It's what's not in A. So what's not in A? 1, 3, and 5. So A complement is 1, 3, and 5. Right? Is everybody good with that? What is the probability of a complement? Yep, exactly. So it's again going to be the probability of 1 plus the probability of 3 plus the probability of 5. And I think everybody will agree now that this is equal to 1/2, right? 1/6 plus 1/6 plus 1/6. All right. The important aspect about this example is I'm trying to hammer home the difference between A complement and the probability of A complement. A complement is simply just everything that's not in A, right? Just like I said, if A is passing this class, then A complement is failing this class. Right? Is everybody good with that? So therefore, here what I'm looking for is failing the class, or I'm looking for the numbers, not the probabilities associated with it. Here, however, I'm asking for the probability of A complement happening. So then I'm looking for the probability of getting these numbers, or the probability of. Right? Everybody see the difference between A complement, the probability of A, and the probability of A complement? Really, really, really important. So whenever you see a homework assignment or a question on the test is going to ask you very, very specific questions. It's going to ask you, what is A complement? Now, you're going to get the answers 2, 4, and 6, which is A, so that's obviously not A complement. You're going to get an answer choice that's the numbers 1, 3, and 5, right? That is A complement, so that would be the correct answer choice. But you're also going to get 1/2, right, which is the probability of both A and A complement. So you're going to get answer choices that's both A complement and the probability of A complement, and you need to be able to distinguish which one it's asking for. Any questions about that whatsoever? All right, then take a minute for yourself and see if you can do B, find the probability of B complement, and find B complement. Anybody need a little extra time? All right, what is B complement? 1, 2, and 3. And what is the probability of B complement? 1/2, right? Everybody's good that it's the probability of 1 plus the probability of 2 plus the probability of 3, which is equal to 1/2, right? We can either find the probability of B complement like we did this way. This is how we've been doing it so far. But let's also try to apply this probability rule for complements here real quick, which I think is really, really straightforward. But we could have also done this as the probability of B complement is equal to 1 minus the probability of B. And we found out earlier in the previous page, the example on the previous page, that the probability of B was equal to 1/2. So therefore, we could just have this as 1 minus 1/2, and also got the 1/2 that way. So these two things right here, above the squiggly line and below the squiggly line, is the exact same thing. Sometimes, whenever we're working with a large data set, right here we only have 6 numbers, which isn't really hard to do. But suppose that you had like 60 numbers that you needed to do, right? Now, if you have 60 numbers and I asked you to find the probability of B up in this problem, and let's say that it was like 28 out of the 60 numbers, you're going to be like, wow, this sucks, because you're going to have to add up like the probabilities of those 28 numbers. And then if in this problem I'm asking you to find B complement, you can either go add up the other 32 numbers, or you can just take 1 minus the probability that you just added up. So sometimes using this way is going to be a lot easier. Right, does that make sense? All right. Any questions about any of this stuff so far? All right. So now let's get into a little bit more fun stuff. Start talking about intersections. So the intersection of two events, we're going to denote that by A intersection B. So this symbol right here, it's like an upside down U. That is our intersection symbol. The intersection symbol. The intersection between A and B is the collection of all outcomes that are elements of both A and B. And the buzzword that we're looking for in the problems is the word and. So whenever you see a problem that says find the probability of A and B happening, well then it's asking you to find the probability of the intersection, right? Whenever you see the word find the probability of A and of B, that's for the intersection of those two events. So our buzzword for the intersection is the word and. On the next page gives us a picture of what the intersection looks like. Which is right here. The intersection of two events is this dark shaded region right here. It's simply what is in A and in B. Right? What they have in common, where they overlap, that's the intersection of those two events. Again, really, really, really important. I want to stress that one more time, that the buzzword of when we're going to do the intersection for a particular problem is whenever that problem has and in it. Everybody good with intersections so far, the concept of intersections? All right, so let's then, if we go back to this die example, just as a really, really, really brief example up here. What's in the intersection of A and B? 4 and 6. Everybody good? That's 4 and 6. It's just what they have in common. All right. The next definition that we're going to learn is for mutually exclusive events. A and B are mutually exclusive events whenever they have no elements in common. So if you wanted to draw a Venn diagram of two events A and B that were mutually exclusive, what would that Venn diagram look like? Awesome. Two separate circles, and those circles do not overlap. They have absolutely nothing in common. Is everybody good with this? Awesome. Then if we're trying to find the probability of mutually exclusive events, right? So we're trying to find the probability of A intersection B whenever A and B have nothing in common. What do you think the probability of that is going to be? Just 0, right? So if A and B have absolutely nothing in common, and you're saying, hey, tell me the probability of something happens that they have in common. Well, they don't have anything in common, so the probability that something happens that they have in common is just 0, right? Because they're not sharing anything. Right? You can kind of think about it, maybe a real-world example of that would be, let's say that none of us in here have the same birthday, right? And I asked you guys, I said, hey, what's the probability that we're going to celebrate our birthdays on the same day? Well, it's 0, right? Because none of us have the same birthday, so we're not going to celebrate our birthdays on the same day. Right? Does that make sense? So mutually exclusive events are simply just things that don't have anything in common. So the probability of something happening for mutually exclusive events is always just going to be 0. All right. Another way that we can express that is so this is now for the probability of A intersection B. But if we just look at A intersection B, right? So what they have in common. Here they have nothing in common. So there's a couple ways that we can write that. One of the ways that we can write that is we can make 2 parentheses. We can have open parentheses and closed parentheses, and nothing be inside those parentheses, to show that there is nothing inside A intersection B. But another way that we can write that is using this symbol right here. It's like a circle with a line through it. And the circle with the line through it, this is called the empty set. Circle with a line through it is called the empty set. Let me push this up a little bit. It's called the empty set. So if A intersection B has nothing in it, if they're mutually exclusive events, we can show it either this way, we can use it with the empty set symbol, or obviously we can draw a Venn diagram like we just got done doing where those 2 circles don't overlap. All right, how's everybody so far with the intersection of events and mutually exclusive events? All right. Then let's do an example here. Right. So, consider the following sample space S, event A, event B, and the probabilities of those 10 outcomes. So we have the sample space. There's 10 possible outcomes in the sample space. A is going to have the numbers 1, 2, 8, and 9 in it. Event B is going to have the numbers 2, 3, 5, and 6 in it. Event C is going to have the numbers 3, 4, and 5 in it. So let's just stop there for a second. Take a minute for yourself and try to do A. See if you can draw a Venn diagram with these 3 characteristics. We have 10 outcomes, 3 events. We have those numbers in those 3 events. Does anybody need a little extra time? Alright, so let's see here. So we have our sample space, and our sample space has to contain all possible outcomes, and that number does numbers 1 through 10. Then we have 3 events, event A, event B, and event C. So let me ask you this. Do events A and events B have anything in common? Has a number 2 in common. So we know that A and B have to overlap, and in their overlap we're going to have the number 2, right? Do events B and C have anything in common? 3 and 5. So we know that B and C need to overlap, and in that overlap we need to have 3 and 5. Do events A and C have anything in common? No, so those don't need to overlap, right? So we need to have A and B overlap, we need to have B and C overlap, but we do not need A and C to overlap, right? Does that make sense? All right, so let me draw that. We need to have here A, and this needs to overlap with B, and this needs to overlap with C, but A and C don't need to overlap. So this right here is perfectly fine start, right? Then you guys already said that A and B have 2 in common, and B and C you said had 3 and 5 in common. All right, is that the only things they have in common? All right, then what do we still have in A that we don't have marked in there yet? And where am I going to put those? Yeah, just here in A, right? I'm going to have 1, 8, and 9 over here. So it's still in A, but it's not in the overlapping portion of it. Does that make sense? Then what am I still missing from B? 6. So 6 I'm going to put right here in the only 6 part. And what am I still missing from C? So I'm going to have this right here. Am I done? What am I still missing? 10 and 7, right? I still have 10 and I still have 7. So those need to go inside of S, but they're not in A, B, or C. All right, is everybody good with that? So this right here is a perfectly fine example for a Venn diagram for this setup that we have up here. Everybody good with this? All right. So that is A. Then the next thing that it's asking us to do is to find the probability of outcome 5. All right, why would it possibly be asking us to find what the probability is of outcome 5? Yeah, because we have the probabilities for like everything else. It says probability of 1 is 0.1, probability of 2 is 0.8. We have the probabilities for all the other ones, except once we get to the probability of 5, we have a big fat question mark, right? So that's why it's saying here, find the probability of outcome 5. Well, we have the probability of everything else, but we don't have the probability of 5, so what are we going to do? Add them up and subtract from 1, right? We said that if we add up all of the probabilities of all of the outcomes of the events in our sample space, then that should add up to 1 or 100%. So therefore, if we're missing one of them, and we add up all the ones that we have whatever we're left with whatever we are shy of 100%, and that's just going to be the probability of outcome 5, right? So then, what I'm saying here is this. I'm saying that we have the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 6. I'm going to skip the probability of 5 because that's what we're trying to figure out. Plus the probability of 7, plus the probability of 8, plus the probability of 9, plus the probability of 10. All right, I'm trying to be really, really explicit about it. If you add up all of those, what do you get? 0.88. 0.88, which is the same thing as 88%. So therefore, if the probabilities of all of the outcomes in a sample space have to add up to 100% or 1, then now we know that the probability of 5 is equal to? Awesome. So then the probability of 5 is equal to 1 minus 0.88, which is just equal to 0.12. Everybody good with this? Make sense? There's definitely going to be a question like this on your guys' homework and definitely one like this on your test. Any questions about this type of problem? So again, let me be really, really explicit about it. If you're trying to figure out what I'm going to have on the test, this is going to be one of the questions on it. Yes?
Can you write it as probability of 1 plus 2 plus 3 plus like that, or like in one bracket?
So no, because what you're saying here is this, right? Just to make sure I'm understanding you right, let me put that up here. What you're saying, the probability of 1 plus 2 plus 3 plus blah, blah, blah plus 10, right? Well, technically speaking, if you do this, then this is going to be the same thing as, right, you're adding up all these numbers, so it's going to be something like 50-something, right? Or 60-something. So here now, if I am asking you what the probability, well, let me make sure I get this right. So it's going to be 11 times 4 is 44. We're skipping 5, and then we're skipped. So I think this is going to be 50. Is it 55? Four. You're getting 50. You're getting 55?
10 plus 9 plus 8 plus 7 plus 6.
All right. I'll take your word for it. I'm messing up somehow. All right, so it's going to be 55, and this doesn't make sense. By probability 55. So no, you can't do this right here. It's not the same thing. That's what we did down here. But the good part about this is all your questions are going to be multiple choice, so you're never going to have to write this out. But it's still a great question for later on. Right. Any other questions about any of the stuff so far? Yep.
Are the probabilities just kind of made up in this?
Yeah.
I was just wondering how.
I always get that question. I always forget to mention it. Yeah, I completely pulled these probabilities out of it. Right?
Okay.
The only thing that I really cared about is that they all added up. The ones I gave you two all added up to less than 100%, so it's still the right probability. But yeah, you can come up with any numbers that you want.
Okay.
As long as they're not greater than 1 or less than 0. Right? Great question. Any other questions about this stuff so far? All right. C. What is the probability of event A? So if we're trying to find the probability of, we're trying to find the probability of event A. How do we find the probability of an event? Awesome. We're going to add the probabilities of the outcomes in that event. 1, 8, and 9. Do I also add in the probability of 2? Yep, because 2 is definitely still in A. It's in A and in B, so we definitely still include it here. And what does this come out to be? 0.47. Awesome. 0.47, or simply just 47%. Any questions about C? You guys starting to feel pretty confident about this stuff? All right, then take a minute or maybe 2 to do D by yourself. Anybody need a little extra time? All right, so we're trying to find the probability of B. So whenever we're trying to find the probability of B, we write it like this. Which outcomes are in event B?
2, 3, 5, and 6.
Awesome.
Do we have to explicitly write it out that way each time?
No, again, it's going to be multiple choice, so as long as you bubble in the correct answer, you're good to go. And what does this come out to be?
0.4.
Mm,
Did I get it wrong?
yeah, I got 0.3.
Oh, my bad.
So let's see here. So then this is going to be the probability of 2 is 0.08, probability of 3 is 0.06, probability of 5 is going to be what we figured out earlier, which was probability of 0.12, and the probability of 6 is 0.04. And the,
I had my 5 wrong and then I went ahead and did the one digit and change it.
cool. Everybody good with this? Awesome. Then let's go on to the next example. Take a minute for yourself and see if you can calculate out the probability of A intersection B. So what's in A intersection B? 2. So therefore, if we're trying to find the probability of A intersection B, it's the same thing as finding the probability of 2. Is everybody good with this? And what's the probability of 2? What is it? 1.08. Cool. Everybody good with E? All right, then we're trying to find the probability of A complement. Take a minute or so for yourself and see if you can find the probability of A complement. All right, does anybody need a little extra time? All right, how can I figure out what the probability of A complement is? Awesome. So I heard 2 ways. One, I heard that we can take 1 minus the probability of A. We already figured out what the probability of A was. What's the probability of A?
47.
So therefore, probability of A complement is just 0.53 or 53%. That's one way that we could figure it out. Another way that we could figure it out is what? So if we go back to this, right, our Venn diagram, if we wanted to identify everything that's an A complement, what's an A complement? everything that's not in A, right? So if I again try to shade everything that's not in A, then all of this stuff right here is an A complement. Right? Is everybody good with that? So one way that I could figure out then the probability of A complement is I could also take the probability of 6, 3, 5, 4, 7, and 10, add those all up, and that's going to give me the probability of A complement. Right? So I could take the probability of 6 plus the probability of 3 plus the probability of 5 plus the probability of 4 plus the probability of 7 plus the probability of 10, which is just everything that's not in A, all outcomes that are not in A. If I add up all those probabilities, I should again end up with 0.53. Everybody good with both those methods for finding the probability of A complement? All right. Then let's go on to G. We're trying to find the probability of A intersection C. Let's do this one together. What is in A intersection C? Nothing. They don't overlap, right? So there's nothing in their intersection. So therefore, we could rewrite this as the probability of this thing. And what's this thing called again? The empty set. We could also rewrite this as the probability of the empty set. So therefore, this probability is equal to 0. So therefore, what can we say, using a new vocabulary word, what can we say about event A and event C? They're mutually exclusive events. Right? Everybody go with mutually exclusive events? All right. What about the probability of A intersection B intersection C? Take a minute or so for yourself and see if you can identify what is in A intersection B intersection C. All right, what is in A intersection B intersection C? It's not 2, 3, and 5. What is it? It's not 0. It's nothing, right? It's nothing. So you're on the right track, right? That I think what you meant was with 0 being that there's nothing in there, right? But it's not the number 0. There's nothing in there, right? So here, let's think about it like this. In the previous example, we said that A and C, event A and event C had nothing in common, right? Then if I say, hey, if these two things have nothing in common, just because I'm adding in event B doesn't mean that they're going to have anything in common, right? Let's try to take it to a real world example, right? Let's say you have two people up here. Let's say I'm one of the people, and you have somebody else that's next to me. And let's say that I'm from Chicago, I'm a Tar Heel fan, and I live in Charlotte, right? And this other person you have right next to me, this person is from Minnesota, they're a Duke fan, and they live in Durham. Then we have nothing in common, right? Meaning that this imaginary other person have nothing in common. If you bring another person up here, doesn't matter what fan that they are or where they're from, if you ask, what do all three of us have in common? Well, because me and that other person don't have anything in common, all three of us can't have something in common, right? That's impossible to prove. So that's exactly what's happening here. We're saying that A and C have nothing in common. Just because we're adding B up here doesn't mean that all of a sudden there's something in common, right? So we could also say, hey, probability of A intersection B intersection C. Suppose we had another D and an E and an F and so on and so forth. It doesn't matter. If A and C have nothing in common, we can have this huge long list and they're still not going to have anything in common. Is everybody good with that? So therefore, this is also just a probability of the empty set. And here, that's going to be equal to 0 again. Everybody good with intersections and probabilities of intersections? All right. So we'll leave it at that. Real quick, what I'll mention here is this. Well, we're not saying with this portion right here, with this one, what we're not saying here is that A and B are mutually exclusive, or A and C are mutually exclusive. We're not saying anything about their pairwise mutual exclusivity, right? We're not taking them as pairs. We're taking the entire group. So the entire group doesn't have anything in common. But each individual pair, so A and B or B and C, don't necessarily have to be mutually exclusive. Is everybody good with that? That pairwise mutual exclusivity is different than this entire group A, B, and C being mutually exclusive. Okay. All right, then let's move on to the union of events. So the union of events A and B, the symbol for the union of events is like this little U-looking thing. So this is our union symbol. It's helpful that this is the union symbol because that's an easy way to remember it. That the union symbol kind of looks like a U for union, and then the other one is the one for intersection. Okay, that's how I would remember it. The symbol for union looks like a U, and then the other one, the one that's the opposite way, that's going to be our intersection symbol. All right. The union of two events, A and B, are if you take everything that is in A and everything that is in B, and you combine those two things. Right? So it's everything that is in A or in B. So therefore, our buzzword here, this is a typo. This shouldn't be of, this should be or. Anything that is in A or in B. So our buzzword for when we have to do the union of two events is going to be the word or. So if you see a problem that says find the probability of A or B happening, then you know that problem is asking you to do the union of those two events. All right. Now we have this right here with the additive rule for probability, or how do we find out the probability of A union B? The way that we figure out the probability of A union B is this formula right here, the probability of A plus the probability of B. But then we have to subtract out the probability of A intersection B. Now, why are we subtracting out the probability of A intersection B? Well, let's take a look at it here for a second. If we go back to our previous example, how am I going to do this? Let me do it like this. See if that works. Right. And if we're trying to figure out is that on the next page? It is on the next page. We're trying to figure out the probability of A union B. See if I can fit all of this on the same page. I don't know if I'm going to be able to fit all of it on the same page. You guys can see all of it. Hey, there we go. Making it work. All right. We're trying to figure out the probability of A union B. Then what we're trying to do here is we're trying to figure out the probability of everything that is in A and everything that is in B, or a better way of saying that is everything that is in A or everything that is in B, right? So we want to have those two things completely combined. So we're trying to find this entire shaded region right here. Well, what this formula is telling us to do is it's trying to tell us well, let's skip using this formula here for a second. So let me backtrack on that right quick. If we're trying to figure out the probability of A union B, if we just use the method that we were trying to figure out that before, one of the ways that we could figure that out is taking the probability of the number 1 plus the probability of the number 8 plus the probability of the number 9, right? I'm simply just adding up all of the probabilities of the outcomes in both A and B, right? Plus the probability of 2 plus the probability of 6 plus the probability of 3 plus the probability of 5. Those 7 are all of the outcomes that are in A or B. Right? Does everybody agree with that? Everybody go with that? All right. Take a minute for yourself and see if you can do this arithmetic and see if you can come up with a number for this. What'd you get? Awesome. 0.69. Everybody good with 0.69? All right. So that's just figuring out the probability of A union B, the way that we've been doing it since the beginning of chapter 3, right? The way that we first learned at the beginning of chapter 3 is how do you calculate out the probability of an event? You add up all the probabilities of the outcomes in that event. So that's just what we did right here. Where the event is simply just the union of A and B. Well, if we look at this formula, let's use this formula now step by step. The first thing that we need to do in this formula is figure out what the probability of A is. So if we want to figure out what the probability of A is, how would we figure out the probability of A? If you wanted to show it step by step, you would do what? Add up all the probabilities in A, exactly. So we would just have the probability of 1 plus the probability of 8 plus the probability of 9 plus the probability of 2. Right, is everybody good with this? And we said that this came out to what? 0.47. The next step in our formula is to find the probability of B. So let's find the probability of B. If you want to figure out the probability of B, you're going to take the probability of 6 plus the probability of 3 plus the probability of 5 plus the probability of 2, and that's going to be what's in B. Right, is everybody good with that? We already figured this one out. What's the probability of B? 0.3 or 30%. All right. Well, now let's compare these two things. Let me push this up. Let me compare these two things. If we compare what we have up here to what we have so far in our formula, what do you notice? What do you do? What's the difference between what we have up here and what we have right here? Right? Here, we only added in the probability of 2 once, but here we added in the probability of 2, and here we added in the probability of 2. So if we just add up these two numbers, 0.47 and 0.43, we're going to end up with 0.77. But what we also did was we added in the probability of 2 twice. Why did we add in the probability of 2 twice? Well, we added in the probability of 2 twice because 2 was in the intersection of A and B, so we added it into A, and we also added it into B. Right? Is everybody good with that? But if we're just trying to figure out the probability of A union B, so if we're just trying to figure out this probability right here, probability of A union B, Well, then what we want to do is we only want to have the number 2 in here once. So what we did up here is completely correct. So therefore, in order to correct this, what do we have to do? Subtract out the probability of 2, or another way of saying that is subtract out whatever is in their intersection. Does that make sense? So that's why if you go back over here to the formula, we don't just add up the probability of A and the probability of B, but since we added the number 2 twice, which is in their intersection, we have to subtract out one of those 2's, which is why we have this correction right here. Does that make sense? So therefore, the probability of 2 is equal to, what's the probability of 2? Probability of 2 is 0.08. So therefore, if we take 0.77 and subtract out 0.08, well, lo and behold, we're going to end up with 0.69, which is exactly what we got up here. So a lot of times whenever people first see this formula right here, they're like, well, if I want to figure out the union, I can just add up the probability of A plus the probability of B. But then when I say, no, you also have to subtract this out, a lot of times I get, well, why do we have to subtract it out? Is everybody good with why we have this subtraction right here too? Because we've added the probability of 2 in here twice, we have to subtract out one of them.
We could just do it the top one.
You could just do the top one.
And just know that's all it is.
That's exactly right. That's exactly right. Yep. So, you're right, doing it this way is completely fine, knowing that each one of these outcomes are only going to be in there once. The only time where it's going to become easier for you to probably do it using this formula right here is, again, if you're working with a ton of numbers, right? Like we already calculated out the probability of A and the probability of B. So therefore, if you're working with 300 numbers or something like that, finding out those two probabilities for A and B is going to probably be time-consuming and tedious. So then if it's asking you to find out the union of those two things, you can say, hey, what do they have in common? Let me subtract this out instead of adding a whole bunch of numbers back up again. Yep. But if you're just working with a few numbers, whatever works for you. All right. What about the probability of A union C? Take a minute for yourself and see if you can find out the probability of A union C. Anybody need a little extra time? All right, so there's two ways that we can figure out the probability of A union C. What's one of those ways? Awesome. So one is we could use the formula. The other one is we could add them all up. So here, if we add them all up, we're going to get, oh gosh, I just moved that away. Let's see. we're going to get the probability of 1 plus the probability of 8 plus the probability of 9 plus the probability of 2, which is A, plus the probability of 3 plus the probability of 5 plus the probability of 4, which is the probability of B. So this right here is the probability of A. This right here is the probability of C, rather. If we add up all of these things, what do we get? 0.76. Is everybody good with that? Even if we use the formula, we would still have done this, and we still would have done this. And if we use the formula, what's the last step that we still have to do after we add these two? Subtract the intersection of A and C. And what's in the intersection of A and C? 0. So then, even if we use the formula, we're just subtracting 0 after this, so we still end up with the exact same answer. Right? Everybody good with how to find the probability of A union C? How do you guys feel about unions? Good stuff. All right. So now that we got this far, so I noticed, and somebody mentioned this to me like 2 classes ago, but I completely forgot to correct it. These notes that I posted on here for Chapter 3 are the wrong notes. And you can obviously see that they're the wrong notes because here in this next example, well, let's just work through the next example and then we'll see why it's wrong. But suppose the respective probability of being elected into office are provided below. So you have different candidates. You have male and female candidates. And here your male candidates are J, J, B, B, and M, M, and your female candidates are H, H, and C, C. And then it says here you have the probability that these candidates are going to be elected into office with these probabilities. And obviously one of the probabilities over here is left off. So therefore the first question is asking us to find the probability that CC will be voted into office. And how would we go about finding out the probability with which CC would be voted into office? Add them all up and subtract from 1. And if you add them all up and subtract from 1, what do you get? Yeah, 0.3, right? Which, like, this is definitely not supposed to be there, right? So I was kind of going along with it all class because the notes are the wrong notes, but I've kind of been making them work. But now we're getting to the point where like stuff is just not really working out anymore. So everybody's good with how we should get that this is going to be 0.30. And then if it says what is the probability that a female candidate will be voted into office, how will we figure that out? Exactly. So here what we're going to say is that if we want to have a female candidate vote into office, what we're asking for then is one of these 2 candidates to be voted into office. So you can think of this as like an event, right? So you can think of this as like, maybe I should have made a circle around this instead of a square. But the way that we're going to figure out the probability of an event happening is we're going to add up the probabilities of each of the outcomes in that event. So we're going to add up 0.2 plus 0.3. That's going to give us 0.5. Right, is everybody good with this? All right. So what I'll do then for next class, so we're going to continue down here with conditional probability. We'll get through as much as we can with conditional probability. What I'll do then for next class is I will print off the pages that you should have had along with your notes. I'm not going to ask you guys to go print them off. I'll print them off for you because there's a couple of things, a couple of problems that we skipped that I still want to do, but I'll bring those to class. And I'll also post those to Canvas. So we'll backtrack here a little bit next class. But I think you guys are getting the gist of these types of problems that we've been doing so far. There's a couple in there that are a little bit different. The wording is a little bit different, so I want to make sure you guys are familiar with that wording too. So we'll backtrack a little bit next class. But for now, we can go on and we can talk about conditional probability. Conditional probability of event A given event B is denoted by this right here. So it's the probability of A, and then you have like this vertical line, and then you have the B after that. The way that you read this is you read it as the probability of A given B. So this vertical line right here is read by given B. Given or given that, it's virtually the same thing. So the probability of A given B, or the probability of A given that B has occurred. So let's try to think about what conditional probability means. Suppose I ask you what the probability is that you bring an umbrella to school, right? If I ask you what the probability is that you bring an umbrella to school, you're going to probably be like, it's probably 2%, right? Like very rarely probably happen. But now if I say, all right, so that's the probability of you bringing an umbrella to school, so that would be something similar to probability of A, where A is just defined as you bringing an umbrella to school, right? But now what happens if I say, hey, what's the probability that you bring an umbrella to school given that you know it's raining outside? Well, now we're maybe at like 50%, right? So what's happening here is that I'm giving you an additional piece of information. I'm saying that, hey, you know it's raining outside. And what that does is it changes the probability that you're bringing an umbrella to school, right? So whenever we have a conditional probability, so this is bringing an umbrella, or the probability of bringing an umbrella. And this right here, the probability of A given B would be to bring an umbrella knowing it's raining outside. First of all, does everybody agree that for most people, right, maybe this doesn't apply to you, but for most people, that these two probabilities are going to probably be a little bit different. Or at least for some people it's going to be. Maybe it's not even most people. But for some people, that these two probabilities are going to be at least slightly different. Right? And what's happening here is that we're given an additional piece of information, and that additional piece of information is event B. And event B is that it's raining outside. So what conditional probability does is this. It's basically giving us a new knowledge, knowing that event B has definitely occurred, or the fact that it's definitely raining outside, and how that changes our probability. Everybody good with what the overarching picture of conditional probabilities, right? You're conditioning on the fact that you're given an additional piece of information. So our formula for conditional probability then is on the next page. And our formula for conditional probability says, if we want to figure out the probability of A given B, then the way that we can figure that out is find the probability of A intersection B divided by the probability of B, right? You know how to calculate out the intersection of two events. We've now done that several times. And you also know how to calculate out the probability of just an event. We've done that a whole lot of times. So the way that we're going to figure out the conditional probability of A given B is we're just going to do this fraction right here. Right? Does that make sense? All right. So are there any questions about the overarching picture of what we would have to do if we wanted to find the conditional probability of two events? Everyone's good with it? All right. Then we'll leave it there. I'll print off those pages that I mentioned, which also obviously has some examples with this, and we'll pick up here and discuss. Yes? No, homework's not going to be due tonight. So I will change the due date of the homework assignment. For the time being, I'll change it until tomorrow. And then what we'll also do is we'll look to see how far we get